I'm sharing. I'm sharing the screen, but you don't see it.
Oh no. Hey, it's on Zoom.
Okay. All right. So despite telling Tony, Jade, and Marek that I didn't want to do anything at this meeting, they put me in charge of the discussion, the multi-messenger discussion that I renamed the multi-messy discussion. All right. So if you are on WhatsApp, you should have received a message with a link for the Padlet. We're going to use the same one? Yes, and no. And I can share also a QR code here, which I have to find. Where is the QR code? Oh, it's in the share. Wait. Share panel. Get QR code. There it is. I'll give you a minute or so to get into the Padlet, and then I'll explain how we're gonna proceed. Are we good? Okay. All right. Okay, the subtitle of the Padlet is I felt some heat. Was it a burst of GW's neutrinos or photons? All right. So since we are all here in the same room and we do different things, we do multi-messenger things, we have neutrino experts, gravitational wave experts, photon experts. You cannot. Which chat? Which old way? Wait a second. You cannot put comments? Comments is on. Post fields. It should be in the WhatsApp chat. You can comment on that message, but you can't post new messages. You cannot post messages on the Padlet? So we can reply to that post. That means post feed? No, this is okay. You need to put, yes. Because you see here, you need to select an option here, which is what I was going to say, in order to post. And the options are GW to new to GW, EM to new to EM, GW to EM, depending who you want to ask. So if you have a question from GW side and is about neutrinos and you want to ask about neutrinos, you have to choose GW to new. Everything. There are all combinations there. All right. Come on, you integrate Einstein equations and the hydrodynamics equation. You can do this. Yes.
The fact that no one is able to is a statement.
What? Yeah, but what are the settings? Don't pause. I don't see any settings. Let's see. It's not clear paths.
Well, we can do a TikTok.
Maybe we can.
Of the
I don't know what.
You want me to start?
I don't know. I don't see. I don't see any. Okay, we can remake the board. Ah. Uh-huh.
Hi.
Okay, try now. Yes. Okay, now you should be able to post. I told you it would have been messy. Multimessenger. Can you post? Ah, okay. All right. Oh, I see there. Okay. All right. So this is your opportunity to ask questions to experts in the room about things you do not know or you want to know. If you behave, at the end, I posted there, I asked AI to generate a picture about a neutrino, a photon, and a gravitational wave walking into a detector. And if you, at the end of the session, if you bear with me, I'm going to tell you a joke about a gravitational wave, a photon, a neutrino walking into a bar. Okay. I'll tell you, it depends on the reaction of the audience. All right. Okay. So I'll give you a few minutes. You can start posting, and then we'll take it from there. It's difficult to read. I'll read it. So I see a lot of people typing on their phones. I don't know if they are actually typing questions or just checking the latest news. Yes.
Can I ask a question to this one question? This okay. Now? Yeah.
Yes.
Okay. So question to a question. This thing of when should we define the time of the gravitational wave signal so we can give that to astronomers or whatnot? Does that matter? It's like plus minus 1 second, and then we have a shock going through a star. And for detection of optical supernova, does a second matter? I would say no. So is this really something we need to worry a lot about? I don't know if anybody wants to follow up. This is more of an opinion than a question, maybe, but I don't think it's super critical when we define the time of the signal.
The time of the gravitational wave signal.
Isn't it critical for the electromagnetic follow-ups?
No. And if it's about a second, I think.
I can take the pink question.
The pink question?
Wait, yes, wait a second. Let's finish this. If it's of the order of a second, I think it would be okay. The shorter the better, right? So in principle, the flying time of the signal between the two LIGO detectors is fractions of seconds, right? 7 milliseconds. But if that is the uncertainty, that it's okay. Yes. I was distracted by.
So I'm going to try to say a comment about unique tiger. Is unique tiger? Okay. So this is something that we ponder every week, and we have weekly call to discuss these things. And so currently we try to do an interpolation to find the time of the shock breakout only if the homologous phase is sufficiently sampled. And we check what is the uncertainty in the extrapolation to decide if we like it or not. If we don't like it, we just let the data to be processed as part of the whole sky search. The other part that can be improved in the future, and we actually ponder it all the time, is that currently we use an upper limit of 5 days in the delay between the gravitational emission and the time of the shock breakout, and maybe that can be improved. Something else that I wanted to mention, which is related to what Rosa covered in her presentation, is that what if we have a light curve that is well sampled but doesn't have the peak, and instead we have an observation later in the plateau or in the exponential decay due to radioactivity. So those two scenarios, there are methodologies that could be employed, even if we're not currently use them. We could use some version of the expanding photosphere method, or we can use the crossing of different bands. And so currently we are not testing, and one of the reasons why we are not testing them is because the observer are doing a little bit better in catching the core collapse supernovae early enough. We had a study done in 2010, and in those days, within 20 or 30 megaparsecs, it was a very small fraction that was caught in the first week of 10 days of the core collapse supernovae. And I believe now the fraction is much larger, and that's why for most of the candidates we have been able to just do the interpolation. But if we would have a very interesting supernova that is not caught early enough, maybe because the telescopes that cover that part of the sky are not on, which it did happen, we would probably try to use the other methodologies. And there are anyway part of the activities that we want to do is just that we started to, I know, gel up one thing at a time.
Thank you. No, so in this regard, and I was talking to Michele the other day. Yeah, so right now this 5-day estimate is based on you have stellar evolution models. You go through the whole stellar evolution depending on the initial mass, and then you estimate how the shock will propagate through these stars, and then you have an estimation of what is the time delay, which you can use as a window to set that. So now, on the other hand, from the light curves, I understand that people is trying to understand what was the mass of the progenitor star. So that which kind of involves a stellar evolution plus the modeling of the light curves. So it's like you are going forth and back in time using a stellar evolution, when what you really want to know is the star that you are seeing exploding and is producing a light curve. And you can measure things about that, like nickel productions and things like that, or mass ejected, maybe. You want to know what was the travel time of the shock within that. So can we skip a stellar evolution just to eliminate an uncertainty and just try to get what could have been the travel time inside the star just by looking at mass ejecta and properties that we can measure directly from the light curve? And this is a question to the people working on light curves and supernova explosions and this kind of things.
All right, I see there a question from Bold Gecko.
Someone
EM.
want to answer the
Oh,
Pablo?
I got distracted. Okay, go ahead.
No,
no.
I'm asking if someone wants to answer, not before we move on.
Yes.
Probably no. Okay.
I can't clearly multitask, right? Listen and think. So the question about how do we find disappearing massive stars to do a targeted search for their gravitational wave emission. We also do all sky searches, right? Completely agnostic in LIGO and Virgo. So even if it's not targeted.
But they're not currently part of the targeted search.
Yeah, they are, but there are untargeted searches, right? So if we get, we don't need to have it targeted. Yes.
And then to add to Bald Gecko's question, or to the answer, so twofold. First, even failed supernovae, these just form black holes with no explosions, more silent, would have some electromagnetic signature because the drop in potential in the central core, as it were to form a neutron star and then a black hole, would launch a weak shock that would travel at the speed of, it would launch a, the change in potential would communicate some energy to the outer envelope and unbind some of the hydrogen envelope and liberate energy that's around 10 to the 47 erg. So even in this case, you could have a weak signature in ENM. And then there's also some evidence that there's with some cadence pre-collapse mass loss from this outer envelope before the core collapses in the months, maybe years before core collapse. So that could also be some indication that a supernova is about to go off, even if it were to be silent afterwards. You have these two channels for possible detection of failed supernovae, even if they're more silent than you'd expect.
I guess there's also a possibility that the star might have already lost some of its outer layers, I don't know, from binary interactions or something, in which case maybe you'd be less likely to have some weak transient. Well, I don't know, do you? Like, yeah, but you would have had to have been already looking at it before, right?
Even for these weaker envelope ejections, this is the well-known Nadesian Lovegrove effect. I can't remember if it's 46 or 47 ergs. These would these should be seen at megaparsecs with all sky surveys. So it wouldn't be targeted. You would see it on all sky survey with some trigger, and then you could follow up on it and look for archived data.
About the data for 2023 IXF, they should already be, the data should already be public. Oh, because it was in the, well, that should not have happened because it's when the paper is out, the data should be out. So
this should happen. You have to publish the data at the same time, but because it was
oh, because okay. Oh, there was no detection. I missed that. Okay. Yes. Anyway, it will be. It will come out in August then, because in August there will be the release of O4A data, the entire chunk. So. Okay, there are a lot of other questions that has not been answered. There are questions for neutrino people, for EM people. There is a question for Thomas. Failed supernova.
At our trial, I gave the answer yesterday, and Thomas said after I answered that that he was going to say some stuff. So, there. That's okay, Tom.
Oh, I'm without glasses, so it's very dangerous.
Hello, everybody. Sorry, I'm absolutely uninformed about what yeah, which of the 20
Can you summarize what's your opinion on the relationship
between the
frequency?
changes with respect to the ongoing direction? Axis of the sun. Oh, good. Okay. Yeah. Good. I can of course only echo what is in the literature about it. I don't recall a detailed analysis which we did systematically for variation for varied models, but the canonical thinking which was mentioned a couple of days ago is already that the SASI frequency is about twice the neutrino modulation frequency, which makes sense because we have neutrino emission correlated with the accretion, and the accretion with respect to the direction of viewing is of course one on one side or on the other side, and you see mostly one side, whereas the gravitational wave emission is visible for both back and forth motions of the shock wave. The spiral SASI, again, is a different issue. The spiral SASI, and Tony mentioned that 2 days ago, the spiral SASI may show a correlation on the same frequency because you have this motion around an axis, and this motion around an axis correlates the neutrino emission frequency with the gravitational wave frequency. So the situation may be different for spiral and sloshing SASI. It's not such that three-dimensional models just show spiral SASI motions. They can also show sloshing SASI phases. They can alternate, they can be interrupted by some convective phases, so not continuous emission of one sort. So all that is possible. Now directionality, yeah, it depends to a significant extent. How large these amplitudes are depends to a significant extent on the viewing angle. When you look in the plane of the spiral SASI, you have the largest amplitude of modulation. When you look perpendicular, you will see a more continuous emission with a smaller amplitude of variation. But it's not absent completely because you have still some fluctuations of the accretion rate onto the neutron star. The amplitude is direction dependent. And similarly for the sloshing SASI, when you look in the direction of the sloshing, you have the largest amplitude of the fluctuation. And when you look perpendicular, you get a gravitational wave signal, but the modulation in the neutrino signal is smaller in amplitude. It's a really complex, I would say, that is certainly worth being systematically investigated, and maybe also with respect to the signal, neutrino signal and gravitational wave signal correlation being systematically explored with respect to detectability. I think we have data in our data archive, the core collapse supernova data archive, data analyzed by Irene Tambora for different viewing directions of SASI as well as neutrino signals. So if you want to do such an analysis for a couple of models where SASI and spiral SASI and neutrino signals are available in 3D analysis, then you can get some data. I think 3 or 4 models, models for such Somebody talked online, yeah. So is the question answered? Was a 5-minute speech? No, nobody says anything, so. Tony, you want to add something?
Yeah, that's perfect. Thank you. Before you came in, I told them that, you know, I had answered the question the other day, and you said you would have said the same thing. Anyway, we'll repeat it again. One thing I want to point out that I think is helpful, it's always good to also go back and understand the physical mechanisms at work here. So just for the record, the 2003 paper is the sloshing SASI paper. The spiral SASI paper is the 2007. And so I think that's when the spiral SASI was first, put forth in the literature. And they're very different beasts. And you don't see the spiral SASI in 2D, but you do see it in 3D. And as Thomas said, you see the sloshing and the spiral in 3D. The sloshing, you have a situation, the shock is sloshing back and forth, so to speak. Of course, in 2D, it's pinned to an axis. In 3D, the sloshing, the sloshing axis precesses, if you will. And you can basically understand intuitively how that's going to modulate the accretion onto the protoneutron star in a low frequency way. And, the spiral SASI is a very different beast. The spiral SASI actually can lead to a triple point. You wind up having, to Chris's point earlier, you wind up having a spiral shock wave that is able to, you have a spiraling flow within the post-shock cavity that is spiraling around, and you can develop an internal shock forming a triple point with the original shock wave. And at that secondary shock, accretion winds up being funneled onto the protoneutron star surface in a very particular way, in a very particular direction, with a very particular frequency associated with the propagation of that secondary shock around. So. Yes, with the SASI frequency. So Thomas is exactly right. And I'm just adding to help visualize intuitively why this is the case. Because in one case, you just have sort of a sloshing modulation of accretion. And in the other case, you have a secondary shock that funnels accretion along it onto the PNS in a very particular way, sweeping around. And it's very easy to picture that. What's very important about the spiral SASE, and of course, you know, these were discovered in idealized settings that were informed by the real thing. But of course, the models have demonstrated their existence. What's amazing about the spiral SASE is that you can wind up, you can start with a progenitor that is not rotating. You conserve total angular momentum in your simulation at 0. And you can wind up with a PNS, a neutron star spinning at, you know, millisecond, well, in a range within the observable range of pulsar periods. Total angular momentum 0, compact object that's born is spun up to a range. And it's very simple to see, intuitively see in your mind's eye how that happens, because if you have this secondary shock spinning around, it's funneling in flows, and you wind up with 2 counter-rotating flows that conserve angular momentum, sum to 0, but yet the accreted flow onto the protoneutron star is spinning up the protoneutron star. So Tomas is exactly right, and I just wanted to add to that to provide an intuitive physical picture, and also to mention to the community, because I think the 2007 paper has been a little neglected. So. One further sentence to IGWN.
Can I just add on that before we get into a longer discussion? This question was actually answered in one of the talks today, and if you want to see how this correlation between the neutrino signal and the gravitational wave signal looks as a function of observer direction, there's a paper by Marco Drago and collaborators where we actually show this. And if you want this data for the other models that Thomas mentioned, I have this data and I've looked at it, and it's similar to the model that we saw in the paper.
Yeah,
so that's
you said my sentence.
Okay. Yeah. Okay. Sorry for interrupting, Thomas.
Are you going to answer one of those questions?
Yeah, I wanted to answer to a different question that Thomas had before, and Jade already had some comment, was the one, are we gonna run in a risk if we have the core bounce of a rapidly rotating or something like that at 10 kiloparsec. And one of the things is going to happen when we go with the 3rd generation interferometers, we're going to detect so many binaries that the chances that one of them doesn't get classified and we say, oh my gosh, it's a supernova, is not going to be negligible. So we will have to be, our colleagues that work with the binaries, they will have to be very good in making sure they catch them all, because if they are in doubt, we're going to be the next in line thinking it's our gravitational wave. Yeah. I mean, if there's no neutrino emission.
Yeah, I was just going to comment on Michele's point. If it's 10 kiloparsecs, though, we will have a neutrino emission associated with it, which will not be a binary black hole. The neutrino detectors stay on more than the gravitational wave detectors.
When I went to Amaldi last week, there was like one session where people were giving supernova talks, and there was lots of waveforms showed. And there was somebody there who works on, they look at the LIGO data in low latency when there's alerts to check that everything is okay, the data quality. And they looked at the supernova waveforms and said, if I saw that, I would have thought it was just detector noise and I would have vetoed it. At which point I was like, oh my God, don't do that. So I think we need to tell some of the people who work on the data quality as well, like, this is what supernovae look like. Please don't tell everyone their noise, because, yeah, we don't want that to happen.
With 2 detectors, it's not going to happen, right? If there is a signal which is coherent then between 2 detectors, it's not going to be vetoed. Yeah, what?
Pipeline just, if it's applied on like Cat2 vetoes or whatever vetoes, so the pipeline don't even run on those data, is it possible?
Well, I'm going to give the microphone to Marek, I'll say that it really depends. If it's only a gravitational wave event and there is no other messenger, it's going to be tricky. But if there is a neutrino signature or something else, it makes it.
Yeah, in a low latency, there is no human involvement. So offline, somebody can do it. But if the trigger is created in low latency, then that's like a different story.
Well, if you remember the story of 1708-17, it was vetoed online, right? It was recovered after that. So again, if there is a neutrino burst or if there is something, people will go and look back into the data. But if there is not, and it's in a cut too, anyway, would you trust it? Probably not, right? So.
There are a couple of questions. Can I take the liberty to just try to answer a couple of them?
Yes.
Okay, I see a new question. Probably, what is the time delay between the core bounce and the neutrino burst, this electron neutrino burst, I assume, which is a spiky feature in the signal that is meant with a neutrino burst. That's just a millisecond. So from the bounce to the breakout of the shock and the release of this electron neutrino burst feature, it's about a millisecond only to reach the onset or the increasing wing of this peak, and maximum may be reached after about 2 milliseconds.
And that would be the delay between the gravitational wave signal and the neutrino signal, right?
The first gravitational wave signature may actually come earlier when we have a core bounce signal from a rotating progenitor. Then the first signature may be this millisecond or 2 milliseconds earlier, actually.
Okay, but it's on the order of milliseconds.
Yeah. The width is certainly that, yeah. But yeah. It's milliseconds. And the prompt convection comes, I would say, at about the same time sets in the prompt convection as this peak feature is. I see another question. What can the detection of gravitational waves from core collapse supernovae successful or failed tell us about gravity beyond GR? I haven't thought much about that, but I would say very little, because we have a really dirty environment. I'm guessing that we are dominated by so many features which cannot be interpreted unambiguously, that it will be very difficult to draw conclusions on non-standard GR physics.
It's an excellent question, and I wish we could say more, right? But it will depend on the event too, because it'll depend on how strong the strong field gravity is. So you can imagine events in which neutron stars form and events in which black holes form. And I think, obviously the latter case is more extreme. It's, potentially more rare, but still a dirty environment. But certainly it would depend on the event itself.
And the detector noise, right? Remember that these things will be, yes. So yep. We cannot even.
I mean, there's several aspects to this, right? Because you could actually see something fundamentally different. Like suppose you see different modes, different polarizations, and then the gravitational wave polarization. I mean, depending on the number of detectors, where in the sky, there's many ifs, but a single detection could give you, signs of alternative polarizations. So I would not completely say, okay, we can't say it, but generally, if we don't believe in such radical changes of GR, then I agree that it may be difficult, but I would never rule out more exotic stuff that then you can immediately see.
The first explanation for it would be some noise in the detector, right?
Yeah. Well,
yeah.
maybe I can say something to clarify. First of all, when Sergei commented about the difficulty of reconstructing both polarization, he was referring to the H plus and H cross because the two LIGO interferometers are mostly aligned. So you pretty much measure one of them. I think the one question that I wanted to have maybe John comment, but is that a few years ago at Caltech, there was an effort to check for scalar polarization that would be produced with a spherical motion, but I'm not sure our interferometer are designed to detect that. So I don't know if it's just a question of how small they are, but also if the interferometer are designed to check for that as well.
So at the moment, it depends on a number of detectors, right? So gravitational wave polarizations, if you assume that there are two following GR, then you need more than two detectors to start constraining them. If you add the possibility that there are more, you need more detectors, right? So yes, but again, in principle, it's visible. We either need more detectors or the event needs to be lensed, in which you see multiple copies.
I think one important thing to add here is that we have to be able to learn something that we cannot learn from black holes. And so we have to, so there's stronger constraints already from binary mergers, right? So this becomes...
Yes and no, because black holes have a very strong quadrupole, it emits a lot. That's why we see many of them. But that also means that it could be obscuring some of the weaker signals if it comes from, let's say, whereas a supernova is much more spherical. So the amount of, let's say, quadrupole would be less. And so if there is, coupling there to the scalar mode, the ratio between, let's say, the different modes may be different, and therefore they may actually be more visible than what you would see for a binary black hole.
I work daily with LIGO noise. So I would say, guys, be happy if you see a supernova signal. Let's not go into testing GR, because even if you see something weird, it's gonna likely be due to the detector, the noise. And if it's not, as you taught me these days, there is a lot of physics into it before getting to violations of GR, right? Oh, yes, of course. Then, yes, you'll have the public data to yeah.
Since I missed a part of the discussion, I need to ask, is this question by Olivia answered already? What parameters of the producer? Okay, that's a very interesting question, because I think there's a lot to say about it, but also relatively little analysis on a solid basis, which I know there's certainly papers. What parameters of the proton star that could usually be extracted, I assume, from the high frequency signal could also be constrained by the neutrino signals. These the neutrino signals are certainly informative about the radius of the neutron star, and also we have a significantly systematic sensitivity of the neutrino energy emitted and the time evolution of the luminosities on the neutron star mass. So I would say mass and radius information for the neutron star could be to some extent also constrained from the neutrino signal. And in combination with a high frequency emission, that may actually lead to better data. That would be my guess. So that's a very promising perspective. The details combining gravitational wave and neutrino signal information probably have to be worked out. I know only papers either in the one or in the other direction, but not combining information from both sides. Anything follow up? Otherwise, I would take a next question left of it. Want to say something?
In one of the presentations, forgive me, I'm just trying to refresh my memory on who it was, who spoke to the neutrino sector and its connection to PNS parameters. They're being shy here. They're not saying anything. Who was that? I'm sorry.
Just to follow up, something I was curious about is how it would affect neutrinos. Could tell us about the mass accretion because or the radius of collapse. So like m dot and r dot, because as the protoneutron star collapses, won't the electrons and remaining electrons and protons fuse to be together to become more neutrons, and that will release more neutrinos? And is there like a way to calculate that steady flux, or would it be overwhelmed by stuff going on with the SOSI?
No. I mean, the SASI measurements, which Tony described, or the SASI emission, which Tony and myself described, this is intrinsically related to the accretion. And you can actually significantly, obviously distinguish the accretion phase from the later phase, which is dominated by the neutron star emission, with maybe a little bit of superimposed accretion signal. I would say yes, with a detailed analysis of the time structure of the signal, maybe with also some information for the emission of neutrinos in different species, which may come from a diversity of detectors. We may be pretty well able to tell the time evolution of the accretion and the separate the protoneutron star emission from the accretion component. Yeah. That's already done. Effort actually is already undertaken in with respect to Supernova 87A. You can believe it or not, but there's a paper. These results. I mean, not the fact that there is. There is a paper series by Visani, Francesco Visani at the Gran Sasso Laboratory, who made efforts to fit, not to calculate, but to fit the 87A neutrinos by a two-component emission, an accretion component and a protoneutron star component. And his claim is that this works, no wonder it's more parameters, but this works much better than an individual component for that signal. I think David.
Yeah. Yes, I just want to add a few more sentences on the possible correlations. We've done in several papers, we've seen correlations between neutron luminosities or the cumulative neutrino energy emitted and the core compactness that gives you a sort of M over R. And also with the neutron star mass, there's a strong correlation. This is absent the clear caveat of what happens with late time fallback accretion. And then separately for gravitational waves, we see a same correlation with the energy in gravitational waves, which you have to get out to a couple seconds because the high frequency feature could last for some time. So you need to have longer simulations here, but that also correlates with the core compactness and also the remnant mass. So in a way, it's almost overdetermined if you can measure any of these. And then in addition, we also found you see the clear correlation between the F modes and the core densities, but there's also a correlation with the cumulative neutron losses normalized by or with the accretion component of m squared over r. So within some 10 to 15% scatter around the mean, you see correlation with the neutron luminosities and this sort of Newtonian accretion, Newtonian binding energy m squared over r, where m and r are again neutron star quantities. So there's many correlations they can just be inspired by. And so in a way, it's almost overdetermined.
The answer is yes. We're really promising to have a gravitational wave and neutrino information for determining or constraining the neutron star parameters. Yeah. Whether it's as good as information from the binary merger, maybe, or from nicer 1 kilometer radius, that's another story.
Olivia, your questions these days have been magnificent, and therefore they spawn a lot of response from the professors in the room. Just, kind of pull back and think about timescales, right? So you form this protoneutron star so that it has this hot shocked mantle and this cold unshocked core. And basically that hot shocked mantle, is going to cool on a Kelvin-Helmholtz timescale. It's going to cool on a timescale of order 10 seconds, during which time the explosion is initiated. And as Tomas said, the accretion eventually is cut off, and then eventually it continues to cool until basically, you have this much more compact, cold neutron star, and you begin to see the electron neutrinos from the very center that have had time then to diffuse out. And so, you know, just to kind of think about the phases, you form this bloated hot object. It cools, but it cools on a time scale almost 10 times the initiation and explosion time scale. And then, you know, even beyond that, you wind up with neutrino emission over minutes, and you enter what's called the neutrino transparent phase, et cetera, and it goes on from there. So just to kind of broad brush it. Make sense?
I would go to the next question if something. Okay, I want to work through the question. So what kinds of progenitor constraints can electromagnetic observations place? That's a difficult question. Unfortunately, Chris has left, I think. Yeah, that I would say there are many constraints, but the question is how good these constraints are. What is the error bar you can attach? I mean, just imagine for a single supernova, an individual supernova measured in multi-band observations over longer timescales so that we can reconstruct the light curve pretty well. The progenitor masses are still uncertain by a margin of 50% up and down. So that's not better, maybe 30%, but that's what the current observations can deliver. And we know, of course, whether it was a hydrogen a supernova with a hydrogen envelope or whether it was a stripped envelope supernova. That's usually, of course, seen by the shape of the light curve and also the spectral lines which we have in some cases, not in all. But the detailed mass and determination depends on the fitting of the light curve, in the better case, the fitting of the spectra or the photosphere radius. But I have not seen data which are better to plus minus 50 or 30% of the mass value. And in supernova 2023 IXF, which was a relative nearby event, there was suggestions between 10 solar masses for the progenitor and 20 solar masses. So you can guess how uncertain all that is. Yeah. Electromagnetic signatures are easy to measure, but hard to interpret. A related question is the one left to that. Has there been a systematic search for Bochum-like events in the core collapse supernova spectra? So the Bochum-like event, the Bochum event in the 87A spectrum was a very peculiar feature, as you see here in a time sequence of spectra. Don't know, cannot read the axis, the time axis, but that was probably over weeks, where spectral line features evolved, and that was indicative of clumpiness in the hydrogen envelope. So there were obviously high density clumps, nickel clumps, which heated the environment and led to a specific extra radiation. And the shape of these clumps, the intensity of the line, could be interpreted with respect to the size and the masses of these clumps. I think I'm not an observer, and I certainly have not followed all the observations of core collapse supernovae in detail and the spectral evolution, but I think that feature has been seen in many supernovae. It's nothing unusual, and in all of these supernovae, there seem to be rather high-density nickel features mixed into the hydrogen envelope, so that we have these signatures also in the spectral line that the hydrogen envelope was contaminated by heavy elements brought by convective motions, by overturn instabilities into the hydrogen envelope. I'm sure that if there is a high cadency evolution of the spectra, that astronomers look for such features, because that's what they are interested in. What kind of elements can they see? How intense is the radiation? Can they measure different masses of different elements also from these line features? Yeah.
I guess my question was somehow related to the ones you just read, because my question was going to be that Rubin is about to observe millions of supernovae, and what can we do with that? What can we learn? How are we going to analyze that many? How are we going to find the interesting ones? What should we be doing?
Did we answer blushing meerkat? yet? Okay, so I know it has been covered over the week, but can someone please summarize what timings can neutrinos and electromagnetic E&M provide together or individually? That is, when is shock breakout, core bounce, core collapse? So we were just talking a little bit about that. Basically, when is core collapse? So, you know, the massive star evolves for of order 10 million years, and it, you know, at one point it collapses, and that collapse happens within a 1/10 of a second. Basically, you then have core bounce, and then within milliseconds of core bounce, you have the neutrino burst. So the electron neutrino burst. You haven't yet produced all three flavors of neutrinos and their antineutrino partners. That gets ramped up very quickly after the initial electron neutrino burst. And then that persists over a time scale associated with the explosion time scale, because it's fed by fuel, by accretion. So it's sustained for hundreds of milliseconds to seconds, depending on the explosion dynamics and the time of explosion and the time when accretion really drops off. And then, of course, the neutrino emissions continue over many seconds as the central object we discussed cools. The shock is formed, and the shock will make its way out through the star and hit the outer layer. Shock breakout can occur anytime between hours and days, depending on the progenitor star. So I don't know if that sort of answered the timing of things, but essentially collapses at the end of 10 million years of evolution. It happens in a fraction of a second. Milliseconds after bounce, you have the Inouye burst, and then for hundreds of milliseconds, you have the three-flavor pulse of neutrinos, and then eventually you get the electromagnetic signature within hours to days.
Thank you. Let me add to what Tony said, all correct. The timescales for the shock breakout, however, need to be generalized. 1/3 of all core collapse supernovae, 1/3, comes from stripped progenitors. So that means a good fraction of core collapse supernovae are no supernovae with an extended hydrogen envelope. What Tony said is correct. It refers to the hydrogen envelope supernovae. There, the shock breakout is between a day after the core collapse and bounce to several days. When you look at a stripped core collapse event, so a star without a hydrogen envelope, the shock breakout can be much faster. It can be within minutes to maybe half an hour. So the timescales vary, but we will know from electromagnetic observations whether we have a stripped core collapse case, a progenitor which had no hydrogen envelope, or whether we had a red supergiant or blue supergiant with a hydrogen envelope. We will know that. It will not be an unknown, observationally unknown property. So we can, if you are interested in how much do I have to go back from the first signature of light, then we might have a guess for you. Yeah. Fine?
We are very.
Yes, I know this. We discussed it years ago in Fukuoka already, how important that is. Yeah. Yeah, there's a.
Hello, that question was actually by me. So if you don't mind, if I can like follow up a little bit. So does that mean that we don't know when core collapse actually happens? Like there's just no signature that neutrino or EM can provide until core bounce happens when the first neutrino burst out. Is that correct?
Yes, I mean, you know, Betelgeuse may have already gone off, right?
Yeah, okay.
So you know, if we see core bounce from the gravitational wave signature, you know, that'll be the first note. Well, forgive me, there's a lot of work being done of late on the pre-collapse neutrino emission, but the hard thing about that is detecting such a low flux of neutrinos. That's a real challenge. But in principle, you know, if we could detect those neutrinos, we would get information. But you'd have to distinguish that from neutrino emission that comes from natural stellar evolution, which gives you the degenerate iron core to begin with, right? But the bounce would be, you know, really the bell, and then we would see the electron, and the gravitational waves would be the first messenger in that sense, and then we would see the electron neutrino burst, and then the rest of the story.
Right. So if we want to search for gravitational waves, we want to search just before the neutrino emissions. Is that correct? Like if we were to have.
Yeah, I mean,
I think I
they
understand.
yeah, of course, you know, neutrinos have mass, and so they don't quite, you know, travel at the speed of light, and their speeds will there'll be some spread in the speeds, but you know, if that's negligible, then yeah.
Right. Okay. Cool. Thank you very much.
Ever the contrarian here, but I mean, you have to ask what purpose are you trying to pursue? Like the timing information for maybe searching for a gravitational wave, the bounce and collapse happens at the same time. There's like 300 milliseconds separating that time, right? So if you want to kind of try to lock down a window to look for your gravitational wave signal, the neutrinos and the gravitational waves, they occur at the same time for all practical purposes. And even beyond that, neutrino emission and gravitational wave physically also is emitted at the same time from the core collapse supernovae. Sometimes earlier, sometimes later, but essentially at the same time. And then when it comes to when, you know, these light curves and shock breakout and all that kind of stuff, it's an issue of the progenitor, but it's also an issue of when the detectors, when the telescopes can actually see the light curves. And these things can have there can be quite long delays between shock breakout and the first light detected in the telescope. So these are also things we need to kind of fold into it. And the uncertainties there are also quite large. And then cadences of service and so on and so forth. So it's more than just a theoretical perspective here.
Yeah, I think I was gonna, you know, take the words out of her mouth that we can see gravitational signatures before core collapse in some cases. Like that's very possible. You can see signatures if it's a convective core before. I mean, sorry, before core bounce, not before core bounce. You can see gravitational waves from 3D progenitors. Yeah, I don't know what the timescales for those are, but that's possible. Gravitational wave signatures before core bounce. Gravitational wave. Yeah, gravitational wave signatures. Yeah, gravitational waves before core bounce. If it's, you know, if there's, yeah, what are the timescales for that? Like tens of milliseconds or hundreds? Before, no, when you would have sufficient convection pre-collapse for a 3D progenitor, sorry, pre-bounce, how far before bounce could you see a gravitational wave signature? Within the core, within the oxygen burning layers and the silicon burning layers.
I would bet a lot of money on that signal being so weak. Yeah, we cannot detect the electric core we cannot detect this happening beam. That was the bet, but this is my.
We've taken his theory badge away. But he's right. In principle, you're right. Right. They would generate gravitational waves, but I don't think we'll see them.
Yeah, I had this data done. It was just purged. It's gone. So I don't know. I do want to try to address Brave Oysters question. So gravitational waves can be asymmetric. In one paper, we did a mole-wide projection where you look at different lines of sight and you can get an estimate for how different the gravitational wave energy could be along different viewing angles. And it could be very different along adjacent viewing angles. It can be. But if you take a small local angle average, we see variance of 10 to 30%. More so, in the first tens of milliseconds, prompt convection should not have a very strong angle dependence because the shock will not have had time yet to develop strong asymmetries. And so, at least for the prompt convection, you should be able to see that almost agnostic of viewing angle. And so I'm not terribly concerned that we will get no signature at all, even in the case of a very asymmetric core collapse supernova where we just happen to be in an unfortunate blind spot.
So I'll preface this with only looking at the D-series models from the Oak Ridge UT group. We also see that the high frequency feature is fairly independent of viewing angle, because these large scale motions, while they may be dominated by plumes coming in and hitting the protoneutron star or whatever other emission characteristics are happening, that's not my field. We do see that feature is almost always the same strength, but it is definitely always there. So if we're looking for something, that's a good one.
I'd like to take Dapper Quail's start. Dapper Quail. Oh, did somebody else have something on? I'm sorry. Are you going to continue, or are you going to take a question? Go ahead. Go ahead, Jade.
I was just going to add to what you said to say that it does change a lot more if you have rotation. But the non-rotating ones, yeah, like, I mean, they do change a little bit at different angles, but not a significant amount. But I mean, we might just have no gravitational waves because the detectors was off.
So Dapper Quail's question, this is a very heavy question, is very, very good one, profound, I think. So how reliable are the core collapse supernova gravitational wave signals to get physical parameters of the source? Okay, so we're doing the best we can. The models have gotten quite sophisticated, certainly in 60 years' time. It's night and day. The models will continue to improve. More and more models will be run, particularly three-dimensional models, and more models will be run longer, particularly three-dimensional models. And so for the time being, you should definitely use what we produce, because it's the best we can produce. It's the best we're going to get. And the models have become sophisticated enough where I think it's reasonable to use them. The other thing is, across groups, across models, we're seeing trends, the right kinds of trends, final protoneutron star masses as a function of progenitor mass, et cetera, that, are physically reasonable. So I would certainly take advantage of everything that we know and can provide on the theory side, with all of the uncertainties that are there, much like on the detection side and parameter estimation side. Again, you do what you can now, given the algorithms you have, given the detectors we have, et cetera. So, I mean, it's the only way to move forward, right? Use everything we have, and the best of everything we have, and the most of everything we have, and just keep going. That would be, so it's sort of philosophical.
I'm going to be the devil on Tony's shoulder here, though. Again, this is speaking just to UTRNL models. Our 9.6 3D model and our 15 and our 25 models look completely different from a spectrogram point of view. Now, we have a lot of reasons why we think this may be. And a point that I want to mention, though, is how often do we expect large burning fronts, large convection happening during collapse that will dramatically alter the way that the core collapse supernova gravitational waves are emitted? Because in our 9.6 model, we still see the high frequency feature, we still see the memory, but there's something else there that is louder, that will blur out the rest of the signal. So, while I agree with you completely, I think we should look into different signals from models, not just prepare for the best case scenario, the high frequency model, but something else from these realistic models that all the groups are producing.
So there's a part of the gravitational wave emission signature that is consistent. Whether or not it will be lost relative to the first, I don't know. I mean, I don't know that we know that, right? Okay, that's possible. But that part is not connected in the way, looking at Pablo and Alejandro's seminal work, and then all the work that has been done on connecting, the high frequency emission, the modal analyses, with proto-neutron star parameters. That is not even that this work that they have started for the community, and we have continued, others have continued, doesn't even really apply there. So this would be, in that instance, we would not, just look in that instance, one would not be able to, in fact, connect the observation with the mass and with even the m over r squared or m over r cubed, period. Yeah, but that's not saying that in cases where the dominant emission is the high frequency feature, that the predictions now are not usable. You're talking about a very different beast. I agree with you that if it's going to wipe out everything else, then in that case there is no connection. Yeah, that we can really.
Just for the records, I object to the use of the word signal in that question. It should be model.
I'm sorry?
Instead of gravitational wave signals, it should be models. We don't have gravitational wave signals yet. Okay. Oh yeah, I forgot about that. Yes.
Yeah, no, I just wanted to comment. I mean, the best simulations are the things that you are doing, the things that Tony is doing, the things that Thomas, Daniel, these are the standard towards which we have to look. But the thing is that if we want to learn something, we have to understand the systematics. We have to understand how it depends on equation of state, progenitors, the neutrino transport that you are using that may be different. There are small differences across many parameters in physical uncertainties that we have and all these things. So currently, we cannot study this with your three-dimensional simulations because it's a limited set and it's going to be a limited set for a long time. So we cannot do the kind of studies that we do. So I think it's necessary to complement that with the things like the things that we are doing, like going to 1D simulations and trying to find the estimations that you can then try to apply to your simulations and see if it works or if it doesn't, just compared to the real thing. But what I say is that it's not going to be able to extract any information, I mean, meaningful information given error bars, just based on the current three-dimensional simulations that we have, that we really have something else to explore systematically parameter space and uncertainties. And these models will have bias that I hope to be corrected in the future just by comparing to the full simulations. But right now, for the analysis of the first signal, we have to get something like this because it's the only thing that we can do right now. And having in control everything. Yeah, that's
Well, have the story in the same room because it's a reality check, right? Thanks, Pablo.
Personally, I think that if we had the gravitational wave signal and it looked nothing like any of our models from the last 10 years, I think that would be really fun because if we measure a gravitational wave signal and it looks exactly like we expected, it's like, okay, we'll go home, we're done now. We're not going to get another one. But if we have one and it looks completely different, then people like Tony can have a field day with the theory on what it is. It'd be much more exciting.
Say what Stan Woosley said when the 1998 VW was on, and it had what 32 times the canonical supernova energy. He was quoted in the press as saying, "I'm going to retire now."
If it doesn't look like one of your models,
It's wrong.
no, Marianne will claim that it's a cosmic string. But oh yes, go ahead. Yes, yeah.
I need to extend this question a little bit. This Depaquelo, whatever that is, how reliable are the core? What is meant by reliable? The models you said, core collapse, supernova, gravitational wave models. If we speak about the components of the signal, I think we have pretty much confidence that these different components, low frequency, high frequency, core bound signal, prompt bounce, convection signal. These signals are there in the gravitational wave emission, but the question is now how accurate are they, or how template like are they? And here, of course, we have and how direction dependent they are. And here we have the big problem. The high frequency component for the proto-Newton star, I said many times now, is probably not so direction dependent. Others are more. But for the high frequency component, I would say we have quite some uncertainty with respect to the frequency, because we don't know the equation of state in detail, so that may shift a little bit. If that doesn't worry you, that there may be frequency differences, I guess maybe you can specify this. There was a point of rotation by Jade. No, good. I mean, if we believe what the stellar evolution modelers and the astroseismologists tell us, stellar cores for almost all of the supernovae, except for a very small fraction, are supposed or are expected to rotate slowly. We are not much endangered by rapid rotation, but it could be, that could be still some ambiguity. Yeah.
So right now, I mean, question of state is what we have done, and Alex will show it tomorrow, and you can get the certainties due to that. But essentially, the relations that we get are quite independent of equation of state.
But I guess you tested the ones which are now the most favored ones for supernova purposes. And this is just a subset of the physics, which is possible. Tobias was making a couple of points of uncertainty here.
Yes, sure. But we're extending now with things. I mean, we're working with Tobias to some more exotic things. So yeah, we start with the standard and then you extend to test something more.
Let me ask a very specific question. Let me ask a very specific question to be quantitative here. We had seen, you presented them, or your collaborators, and somebody else also, relations with respect to m over some powers of r. Yeah. And when there was only proportionality in this factor in front of the proportionality relation, how uncertain is this factor?
Yeah, we have the. I mean, in the letter we have that certain.
I want your answer now. I don't want you to read your letters. There's so many papers I could read that I want the answer now.
10%, something like that.
10%, yeah.
20%. We're talking about.
That's about what I would think.
Yeah,
this is
maybe 20. I don't remember well, but it's around these numbers.
Yeah. Yes. And the question, of course, which I wouldn't be able to answer is that a problem for the gravitational wave detection or extraction, the signal analysis?
We have done the signal analysis. Marianne is talking.
Here.
Marianne did the analysis.
The point of having data, you would measure, I think, this factor. And this is why with data, we would extract information. If it's strong enough, as usual, if we have it. Right. Right.
Basically, in the papers that Tomas is referring to, there are fits, right? And polynomial fits. And the fits are either to the variable x equal m over r squared or x equals square root of m over r cubed. And there are fits. So if we have an observation and we have we use such a fit to the observation, would we not be able to extract not necessarily m and r individually, but some function of m and r? M over r squared or m over r cubed, right?
Yeah, this is, I mean, Alex, we're going to show, you can reconstruct. You can actually, I mean, we have done the injections,
right,
and then do the whole process of reconstructing what is the m over r squared, and then compare to the real simulation, and if it's within the error bars, because, I mean, you have a handle on the error bars because you have done all the systematics, and it is perfectly within the error bars.
Yeah.
So for a galactic supernova, I mean, if it is the signal is strong enough, we are able to reconstruct m over r squared.
Right.
It's something that we have tested already.
Yeah, and something that I like the, the idea that the fits are done, if you're, this is where the modal analysis comes in from on the back, right? You try to learn what physics is going on and whether or not to fit to x equal m over r squared or x equals square root. You do both, and you fit the modes that you believe are G modes to the former and the modes, P modes, or the F mode to the latter. And I know Hajime will speak tomorrow too. I'm looking for, he's done one fit for across the board as well, and finds that the m over r cubed, square root of m over r cubed gives a better fit overall. So this is obviously a work in progress. But the fact of the matter is that if you can make these fits, then you can extract that information.
Yep.
But of course, assumptions about what M is or R is individually, those assumptions that have been made are actually not really, the models don't agree with some of the assumptions that are made to, single out what the mass of the protoneutron star would be, the entire iron core. Some of those assumptions are not borne out by the detailed models and would have to be investigated. But the functional relationship is extractable. Yeah.
And regarding rotation, our assumption now is that most likely there won't be. So we are neglecting it for the moment, but it's in our working plan for the future because it's the next correction that we will want to add after the advection.
For you, my question for you. Rotation. Rotation can mean different things. You can have rotation of the entire object, maybe differential deforming the object. That will have an influence, I guess. I guess it would have an influence on the frequency evolution. Now, suppose you don't have this rotation, global rotation of the progenitor, but what you get is, and that's what we see in our simulations, when you have the three-dimensional convective perturbations in the progenitor, the neutron star surface layers, the accretion layers start to rotate rapidly. Would that have an influence? Because it's this surface G mode contribution which radiates the gravitational wave, so makes the imprint of the gravitational wave. Would surface rotation in a 0.1 solar mass, 0.2 solar mass surface layer cause a problem?
So the first, if the rotation is low, you can actually do it.
The rotation is milliseconds. A millisecond.
Okay, then it will have an impact. Yes. If it has an effect in changing the size of the layer, if it deforms the star or this layer or whatever, it will change.
The deformation is mild, but there is angular momentum. There is just motion of the material which may break the coherence of the wave, I guess.
Well, if it is coming just from this, one simple thing that you can do is if you know what is the gravitational emission from one object, it's very easy to compute what is in slow rotation because it just adds does a rotational splitting of the frequencies. You just have to add and subtract plus minus m the rotation rate and you get it. So in the slow rotating limit, you know what is going to happen, and if it rotates fast and you start having deformation, then you have to do the simulation. Or to get a better analysis because it's certainly more complex than that. But at first level is just rotational splitting. We know what should happen.
Do you see the splitting?
We have not the workforce to analyze all the models for all signals. Sorry, I have a small group which works also in different directions. There's no dedicated workforce for analyzing the gravitational waves in addition to everything else. And I have to admit, there's a numerical problem. If you have in a 3D simulation such rapid rotation, angular momentum conservation gets really poor and you get a deceleration much faster than you wish to have it. Yeah. So it's not so easy. Set up like the one which you do in Valencia, where you can actually impose it artificially and keep it in your system stably and investigate the consequences on the frequency spectrum would be, in my opinion, the desired approach to study the influence of such an effect.
Okay.
Yeah.
Glass is half full and half empty, in the sense that you know, in the case, obviously, if we're dealing with significant rotation, then some of this breaks down. But in the case where we don't have that, then we, you know, have a lot more now than we had a long time ago, right? So I think this is all part of it, working with what we have moving forward, and using it every tool as best we can at any given stage. Now, if the Mother Nature gives us a supernova that renders the application of this type of analysis, you know, difficult, and you know, then we have to accept that, and we won't be able to extract the amount of information we would love from it. But maybe that won't happen, and maybe then, you know, we will be able to extract that information. The one thing I would caution, though, to add to Tomas's remarks, is I would caution the assumptions made about M in order to then be able to extract R in those analyses, because some of the assumptions that have been made with regard to M are not correct. They're not borne out in the models. So we want to be careful about that.
So M and R are just practical definitions. So it's the mass. It's not the mass of the protoneutron star. It's the mass of it's 10 to the 12, 10 to the 11. So you just put a cut at 10 to the 11 gram per cubic centimeter. So you are saying how much mass do you have inside, and how much, what is the radius of this. So this is what we measure. Is this the mass and radius of the protoneutron star? No. I mean, it's not very clear how you define exactly what is the mass of the. So the practical definition, this is just a practical definition, and can be applied to any simulation. So it's something that you can reproduce in any simulation, because you just have to impose this cut, and we're measuring this.
Yeah. Yeah, of course, Pablo, you know, we understand very well the ambiguity in the surface of the PNS, but in the PRL, if I remember right, there's a plot that shows R by itself, and that was under the assumption that M was the ion core mass in the model. So that's all I'm commenting on. I agree with what you just said now, but in fact, one has used that assumption, and so that's the only cautionary.
But I know what you. Yeah, you're right.
Just a quick warning, you're not going to leave this room until all questions are answered, right? So when you are ready to move to the next question, please feel free to do so. Yes.
I have a very naive question to you. When you consider rotation, this means that you start from rotating progenitors, or you assume, for example, an initial solid body rotation in your starting model? It's to all of you. I mean, all of you that.
It depends. If there is a rotation in the stellar evolution model, we prefer to take that. If not, we invent something. Sometimes we also take the liberty to scale up or down by a factor of whatever, to the existing rotational profile, just to explore a variation in that. But usually, if the stellar evolution model comes with a rotational profile, we take it happily.
Hello. I was gonna provide some comments actually. So since you can fit, since you guys have done fits of m over r squared and then square root of m over r cubed to polynomials. These polynomials probably have constants, and since m over r squared, let's say, is squared if it's a quadratic, for example, its units will be different. We'll need to have like counter units to make sure the dimensional analysis lines up. And maybe could that be where the rotation comes in? It could be part of one of those constants. And then also, I think the compactness does play a huge part in the rotation. I read a paper by Pajkos where he said that the compactness can be linearly related to a differential rotation parameter, and that can be and that I think talks about how much of a solid body the protoneutron star is. So I think the study looking more into the compactness could help solve some rotation problems.
All right, quick answer to the observant fly. Is there interest in the supernova group to do an analysis of collapse stars and so on? No, the observant fly, this one. So if the question is for GW people, the short answer is yes. We search for everything. All right. So come and talk. Also, I sense that you are stalling a little bit, like the shock, because nobody's taking Defiant Butterfly there. Yeah. Okay. Yeah. Are you volunteering for that? Huh? I can read the question. Can we set up a data set of gravitational waves, including neutrino data triggers, to test multi-messenger approaches beyond triggered searches?
Yeah. I think we've discussed this already, but this is good to come up again. So, Tomas's group maintains, the data, for the neutrino data, the gravitational wave data. We are now about to, have that public access set up at Oak Ridge National Laboratory, et cetera, et cetera. So the groups are doing this. But to Bernard's good point the other day, and we talk about this tomorrow when we talk about the future and the needs and what the next steps are. The data sets, depending on the data, are enormous, and maintaining data integrity and metadata and all that. It's you have to have the infrastructure, you have to have the people. So the answer is we should. Yes, in the sense of we're already doing that individually at some level, but I think it needs to be elevated to an art form going forward, where any of us in this room could access the data, where the data, the metadata is there, the data integrity is there, and the access to the data is as efficient as can possibly be made. All of the data you might want and beyond is there. We need to do that. And that's going to require, people to organize, to propose to make that happen. And it's going to ultimately require the funding to fund people to actually do that work for us. So to really do this properly is a serious matter. And I certainly can't be on the hook for that. I wouldn't do anything else otherwise. But anyway, we already are doing that at some level now, and the individual groups can be contacted for such data if you need it. Just there's always somebody to call, as we say in the United States.
Right. Yeah. A little statement. I mean, most of it has been said by you, but let me add that, as Tony said, there is some data available on Tony's side as well as on our side. I guess that David also has some model outputs for that. I think that will grow now because the alertness for the interest in such data is coming from meetings like this one. It's limited, of course, by the fact how many 3D simulations we can do, what we can do concerning the data analysis. I mean, one point, for example, which is trivial, you may think, but on our side, it was a constraint for a while. We learned from the first analysis that we need to store the 3D data we do the gravitational wave analysis in post-processing. So we need to store the data with a certain time sequence in certain time steps. And from the first simulations which we did, we stored the outputs every 0.5 milliseconds. And that turned out actually to be not enough because we got a high frequency component of the signal, which we couldn't catch that way. So now we refined it and get 3D outputs every 0.1 milliseconds, which actually grows the data set and data set and data set. It's enormous data amounts. And therefore, this is a trivial limitation. But when you spend 60, 70 million core hours and the old models have such a deficiency, you can't just repeat it. I mean, we cannot run 3D models as David can. I don't know where you get the computer time from, but I heard that the US will shut down the computer centers because Trump has another use for the money. Anyway, these are trivialities. Oh, AI, yes. Yeah, because there's money in it. Yes. But what I want to say is, yes, the data will grow. There is a little bit available for this purpose, but we are not yet satisfied by what we have. Yeah. Let's continue with the, oh yeah, there's more. Yeah.
So I think trying to store in some mega database every person's every output from the simulations would just be nuts because it's like you said on that scale. So I think like when people are talking about some common database, so they just mean more like the gravitational wave signal, the neutrino signal, maybe a few extra things like the mass and radius of the PNS or whatever. You could make a little list, and that at least is more practical. But you know,
but it's also direction dependent. So
yeah.
Just a few parameters. I mean, for a gravitational wave signal, you just need 5 components as a function of time, and you can reconstruct in any direction the signal. I mean, you just need the quadruple components. I mean, it's very few data. What you
I mean, do you include the neutrinos?
No. Well, the neutrinos, okay, yeah. But neutrinos, 800 pounds.
Yeah, so I think.
And then somebody asks you, when you have a neutrino signal in one direction, what exactly is a gravitational wave signature in that direction? I think you want to store both.
Thank you. To help advance the frontier of including neutrino mixing in our environments. You know, many of the folks who are doing that, who are pushing that frontier, are not the folks who are running the 3D simulations, which means that they need the data from the 3D, the neutrino field data, the detailed neutrino field data, multidimensional neutrino field data, in order to do that. So across the board, if we're thinking about, you know, all of these aspects, and they're all coupled together, obviously, we are talking about very serious data volumes. But Jade, you're right. This can be tiered, right? So there could be, you know, low dimensional data that's, you know, as Pablo was saying, is very important and usable, and then, you know, tiered. But at the end of the day, we are talking about petascale data. And I think Tomas is right. These simulations are so expensive that we are nuts in trying to save all of it, because it's so hard to get, to create, and it's so valuable. And I mean, from across the groups that are doing this, I mean, you know, we have to really do this going forward.
So I see young people with their hands up, and I think we should let them speak. So Adrian.
We are also 2 minutes from the nominal end of this session, And there are a few more questions we need to answer. So
I'll be quick.
Be quick.
Okay. So yes, the idea of maybe tiers of on particularity, because I think on the detection side, we don't need as much information as the whole simulation, obviously. I was the one asking the question. And also was why I was asking for data, or maybe there's trigger informations, some stuff like that that we could just use to start getting not full data sets, but just storable amount of data. So sorry, tiers and having discussion back and forth on what we need, what you can provide, I think could get into a way that is storable somewhere. I don't know who, when, but possibly there is a solution with that.
Just as a general comment, because Matteo made the suggestion. So I had when in the discussion session that I emceed, I had a set of questions and we never got to them. And we're going to post that so that people can chime in and begin to fill this out. So just as a specific example, I mentioned that, but generally, and we'll talk about this tomorrow, and this is where the white paper will discuss this. And I tried to sketch out an outline, and Jade and Marek and Marco and I will take a look at that this evening. But the idea is to collect all of this information. So this has been wonderful. And the discussion's been wonderful, but we want to, if we just leave it at that, we're going to all feel good about the meeting and then eventually forget things. So we're going to we want to collect all of these needs, these suggestions, these concerns, these questions, these needs, and ultimately, collect the things that we have, make those available in any way we can now, while we look to the long term of doing it in a more sophisticated way. And, we want to continue to be able to answer questions as we go. Essentially, we want this discussion to continue. In modern day, right, I'm not well-versed in these environments, but we have people that are, and we can facilitate that discussion going forward, even when we disperse. Yeah, so we're going to capture this.
Yeah, I apologize, Jade.
No, no, you won't leave this room until all those questions are answered. Yeah, says Chris, because
we should close
4 of the questions are for DNM folks. No, go ahead. Go ahead.
Okay, so about storing the data and saying that it's petabytes and terabytes of data. So there's a way around this, and you can actually store most of the information in your neutrino fields by way of spherical harmonic expansions. And I've done some experiments with this, and I checked the L numbers that you need, and you don't need that much, actually. You can reduce the amount of data by quite a lot. And I have done this. I tested it on some of Thomas' data, because I did this when I was back in Gashing. And this actually works remarkably well. And I'm again, could bet some money. I could show you the 2 plus next to each other, and you would not be able to tell which one is which. So this like, we could be clever about what we store, how we store it, and what we actually need. So okay. No. I talk about the actual data, the hydro data, the neutrino data, the fields in the simulations. I can show you a plot.
Well, we can. That's fabulous. I agree. Their data reduction algorithms are very important, very useful. The only concern there is that, not to change the data in the meaningful way. And you're fine.
Maybe the conversation can continue in the bar.
Yeah.
Yes. So, yeah. All right. Session is adjourned. We'll see. You can type, we can type the answers to the questions there.
I just have one announcement. If you want to contribute to our focus issue and our proceedings, you should have received an email from me or Marek or Tony or Marco. So if you want to contribute and none of us have emailed you, then come and tell me so I can invite you. Now you can go home.